Hello everyone, we are Team ElShaddai and we are the team members of 5 and our project title is CMN Analyzer. So now let us see about our project. So behind every invention there will be a problem statement. Here is ours. In today's world, modern SoC architectures like ARM's CoreLink CMN-600 generate thousands of data points per simulation. Behind those numbers, a performance bottleneck is silently degrading your system and finding it manually takes hours. We were given 17 output files from a 500 microsim VisualSim simulation. So this is what it looked like. Further, we'll see about how the VisualSim representation will be. This is the CoreLink CMN Cyprus model in VisualSim Architect. So the system has 79 network source nodes and 49 RNF fully coherent nodes for CPU and GPU clusters. On the memory side, it has 12 HNS home nodes and 12 SLC system level cache instances and 10 CXL interfaces connecting to external memory. This simulation runs for 500 microseconds, generating latency, throughput, and coherency data across the full CMN mesh. So this complex data has been converted into a automated pipeline. So next, let's see about that. We designed a fully automated 5-module analysis pipeline. It starts with parser.py, which ingests all 17 simulation output files automatically, including 64 dataset PLT files and the fully architecture stat logs. Then analyze.py then runs 4 independent bug detection engines simultaneously with 0 hard-coded thresholds. Every anomaly threshold is computed from the dataset itself. The entire pipeline runs with only one command by using the run python command. Now let us see about how our dashboard will look like. Our dashboard is automatically loads on the given domain, which consists of multiple tabs. The tab 1 gives an immediate system level picture of 500 microsecond simulation, which consists of maximum end-to-end latency and minimum latency and also have the mean latency. The difference between the two latencies of 10 times bigger, so which indicates something is wrong at the higher end. The component type summary shows RNA interface nodes that are consistently the highest latency class. The tab 2, which have the latency analysis, which will shows about the top 20 components, so in which the RNA 17 leads the highest peak latency. So next thing, the tab 3. The tab 3 represents about the throughput, which will have the 159 gigabytes per second for RNA 41 and RNA 42. That asymmetry in response channel load is a key signal for the bugs we found. Now let us see about the key findings of 4 important critical bugs. So due to the time lag, I'll explain one of the important 2 bugs. So the bug number 1, and this is the critical finding. The RX SNP channel is the part that delivers snoof invalidation requests from home nodes to CPU cache nodes. Without it, coherency breaks. The HNS home nodes confirm generating 23 snoof packets, but most never reach the CPU caches. In a real chip, this would cause stale cache reads, one of the most dangerous coherency violation in SoC design. The second bug, which is all about SLC1, the system level cache, all 12 SLC cache instances shows 99% miss rate, which is expected, but SLC1 has 1,02,000 buffer flows. Every other SLC has around 11,400. That is 9.1 times higher, and this hit ratio is 0.07% versus 0.47% for the others, 7 times worse. This means one cache bank is receiving a disproportionate volume of traffic and a direct consequence of unbalanced address mapping in the SAM configuration. Still now, we have explained about the overview of our project. Now let us have a quick review of root cause summary. The 4 bugs which I have found are not independent, but they form a causal chain. For example, by fixing the address mapping, you can fix the 2 bugs simultaneously. Thus, all the 3 bugs share one root causes, so our system identifies all of these bugs automatically from raw simulation files alone. Our system is not only generating the graph, but also generating how it is happening. In today's world, there are millions of projects coming per day, but the novelty among those will be a bigger question mark. But our system does 4 things that go beyond the charting and the uniqueness. The first one, we are not generating only the graphs, but we are also generating how the error occurs and how to rectify it. The second one, we are not saying the SLC1 has higher overflow, but we are saying the SAM address mapping is unbalanced, so that we can make a sensitive things. The third one, since the pipeline is repeatable, you can upload or drop the new files so that you can generate the newer one within a single command and get the same structured diagnosis. And the fourth one, since it runs under the 5 seconds and there will be no manual steps and no manual interpretation can take place here. And finally, in SOC design, every hours of debugging costs engineering timing and silicon risk. Our system reduces that from hours to seconds. We analyzed a 79 node CMN-600 mesh. We found 4 bugs, including a critical coherency protocol failure, all from raw simulation output files with zero manual analysis. All these things have been generated with an analysis report within of only one click in the web page. So this pipeline is fully automable, repeatable and adaptable to any VisualSim. So we are not just visualizing simulation data, we are enabling intelligence and evidence-based system design. And this is all about Team ElShaddai and VisualSim Electronics Hackathon 2026. Thank you.